Good afternoon. Let's start our session. We have this session about side channel analysis in ISC Winter School on Information Security and Cryptology. I would thank Bob Brumley for making this talk. Billy is an associate professor in the Computing Sciences unit at Tampere University, Finland, where he co-leads the Network and Information Security Group. He's a 2018 ERC Starting Grant laureate. He's a former staff engineer for Qualcomm's Product Security Initiative, and he specializes in cryptography engineering and side channel analysis. I would disable chat during the first minutes of our starting talk, and then I would enable for questions. We have a question and answer part in the middle of the talk, and I will note the questions you mentioned in the chat part. Okay, let's start. Thank you, Billy. You can start.
Thank you very much for the intro. So I'm not really sure what the sort of how deep the talks were yesterday, but I can tell you this talk is more of a high-level talk that will cover work that spans about 10 years. And I'll get into why it spans 10 years in the next few slides. So my talk is going to focus on side channel analysis, but first I want to talk about software development in general. So if you take the software engineering field right now, there's a very big trend in something that's called agile software development called technical debt. So you can see the definition, the technical definition from Wikipedia for what technical debt is on the screen here. I'm not going to read it, but I'll just to give you a high level idea of what technical debt is, especially when applied to a software project. So you have a software project. Technical debt means that you have some feature that you needed to push out into your product, all right? And there's always deadlines, right, in industry. So I guess you're up against a wall and a deadline, and you're just hacking code together and trying to make it work so you can meet the deadline. So that's your number one priority, okay? So maybe you added some parts of the API and you didn't really think about what that API is supposed to look like, but you had, less than a day to finish this, so shipped code is better than missing the deadline. So what technical debt means is you really didn't think through that API very well that you just implemented, and you didn't write any unit tests for the code that you just wrote or the API that you just designed. You basically just hacked up this code and shipped it. So technical debt means that over time, those shortcuts that you took to meet that deadline, so the fact that you didn't write unit tests, the fact that you wrote very poor quality code, the fact that you made up your own API, you have to pay for that down the road. And what I mean is that there's all sorts of technical ways you have to pay for those shortcuts that you took. To give you and what I mean by pay for that, technical debt is like the interest that builds, okay? It's all that, those shortcuts that you took, they're not free, they keep piling up, and eventually you have to pay for them. It's like interest, all right? You have loaned from the project basically, and you have to pay it back. That effort. So to give a very concrete example of how that can happen, let's say that you have invented your own API at the last minute, okay? And this all happens over time. It's a very slow process. So eventually some other developer, either internal to your company or external to your company, they start using that API and they write applications that depend on that API, okay? And if you didn't think out that they don't really care how you thought about that API. This is the API that is offered to them, so they use it. Okay, so then a couple of years down the road, you realize, oh, that API that I wrote, it actually wasn't very good. So you just go and change the API. Academics, you can do that. You just go change the API. In the real world, you cannot just change the API, because what happens? All of those applications that have started to link against that API and use that API are going to have to update as well. So if you have two developers that are dependent on your API, and each of those developers have two developers that are dependent on that API, this is like exponential growth of dependencies, right? So every time, if you decide to suddenly magically change your API, it could be an exponential number of applications that have to update to fix that. That's exactly what technical debt is, right? Think about all this effort to change that API because it wasn't designed well in the first place. That's exactly what technical debt is, all right? So this talk is going to be about technical debt that can start to mount because of poor decisions with respect to side channels and cryptography. Okay, so I'm going to talk about code that has been present in a code base for a long time before side channels were even a concept, to be honest. And so basically, we are still paying off the technical debt for those engineering decisions that were made almost 20 years ago. We are still paying off this debt. Okay, so that's what the talk is going to be about. I'm not going to go too much into the low-level microarchitecture details, but at the same time, to give you an idea of the kind of code that has been implemented and found to be vulnerable, and also what you look for when you're reviewing code for side channel vulnerabilities, I want to go through that process with you. Okay, so I'm going to give a couple of theoretical slides now, but then we're going to switch immediately back into very practical, real-world implementations of crypto, okay? Probably a lot of you are already familiar with the concept of what elliptic curve cryptography is and how you do digital signatures with elliptic curve cryptography. This slide presents the ideas. So the top block talks about a legacy elliptic curve. So you have an elliptic curve that's defined over a finite field, okay? These have been, I guess it's about 25 years now, and at least 20 years of standards we've been dealing with this. That's why on this slide it's called legacy elliptic curves, because we really don't do elliptic curve cryptography like this anymore. Like the modern curves are like these twisted Edwards things, and like we've learned a lot over 25 years is what I'm trying to say. But you can't unring a bell. This is the way crypto works, okay? I know academics, you think you can just move on to the next cool, fancy thing that will get your publication, and then you submit some code off the supercop and you call it a day. But in the real world, you cannot unship and you cannot undo standards, all right? So these are standards that are 20 years old and they're not going anywhere, and you can't just throw them away, okay? So that's the curves on the top block here. If you look on the bottom, it tells how you do digital signatures with one way to do digital signatures with elliptic curves. The notation here, we have the order of the group is n a prime, and then we have a private key that's chosen between 0 and n. You have a public key, which is d times the generator. And then basically all those parameters are fixed, okay? The curve is fixed, and we can assume that the private key and public key is fixed. So when you want to sign a message, it's shown in the bottom R and S values, basically. So you choose a random number k that should only be used once. It's an ephemeral key. And you multiply k times g, all right? And you take the x coordinate of that, and that's the R component of the signature. And then the S component of the signature is on the bottom here, and it's linear. So the way we are going to think about side channels in this talk is, it could be that the scalar multiplication here, this k times g, it could be that the implementation leaks part of k. I don't think that leaking all of k is interesting, because if you know k, if you have an implementation that leaks so bad and you know all of K, then if you look at this second equation here in S, it's linear. And if you know, it's one equation and two unknowns. But if you know K, it's one equation and one unknown, so you just solve it with linear algebra, okay? So you solve for the private key, D. So leaking all of K is not interesting. To be honest, from side channel perspective, it's not that interesting. So we're going to talk about actually small leaks of K. So what happens if you leak a bit of K, 2 bits of K, 3 bits of K, 4 bits of K? So very small amounts of K might leak, okay? And what can we do with that? So when we look at this digital signature, we're going to focus on the linear component, the second component S here, okay? So if we do one digital signature, then we have one equation and two unknowns. So the unknowns are the nonce and the private key, okay? But as an attacker, you know, you can do all kinds of things. So you can query multiple signatures, right? So let's say we get 2 signatures. So let's take the linear parts from 2 of those signatures, and then what do we get? Well, we have 3 unknowns now because you have the 2 nonces, right? And then you have, because the nonce is unique per equation, so you have 2 nonces and you have the long-term private key. So that's 3 unknowns. So you have 2 equations and 3 unknowns. Doesn't really help you that much. So let's say we get 3 digital signatures. You end up with 3 equations and 4 unknowns, right? So in general, you end up with n equations, or I shouldn't say n, but let's say j equations and j plus 1 unknowns. So there's essentially infinite solutions. In this case, there's nothing infinite in crypto, so this is there's n different solutions, which might as well be infinite. So that's why the linear part of ECDSA works. And that's why exactly if you reuse a nonce in the ECDSA, it breaks immediately because it's just linear algebra, all right? Okay. So what does actually the implementation of that top, so K times G, what does it actually look like? I'm going to switch over for a minute for the oldest vulnerability that I'm going to talk about in this talk. And this is the OpenSSL code base. I'll talk more about OpenSSL a little bit later, but I just want to, in this short example, I want to just explain how something might leak. So what we have here is a scalar multiplication algorithm. It's the thing that does K times G, okay? I forget what the function is called. The name is way up at the top here. It's called ECWNAF-mul. Okay, so that's the name of this function. So if we look at the loop, it's basically exponentiation algorithm. It starts at the top digit of K and works down to the bottom ones, okay? So the first thing it does, it's a double and add algorithm. So you can see it doubles some kind of accumulator, and then it is supposed to add some kind of point. The logic for that is kind of convoluted. There's a lot of variable control flow here, but if I scroll down to the actual add, so we did the double before, and here is the add, okay? We can see that to the accumulator, it adds something from a lookup table. And you can see the index for this lookup table is a secret digit. So this is like a textbook method. This is like a textbook vulnerability for a cache timing attack or any kind of side channel attack for lookups into indexing into a table, basically. And the reason is because the speed of accessing this value, this val sub value at this offset depends on the availability of that value in the cache, if it's there or not. So it depends on the microarchitecture state. So this is generally bad. So this is the vulnerability. It's one of the vulnerabilities. I can probably scroll up and find another one. Yes, here is the second vulnerability. So it is only doing this operation if the digit is non-zero, which makes sense, right? Because if you want to add, if the digit is 0, you can skip it, right? Technically speaking, you can skip it. From side channels, you should never skip it because then you're telling the attacker that that happens to be a 0, which would be very bad, all right? So this is real code that has been around for, I don't even know. It's 2021 now, so this code is 16 years old, at least. And, right. So this code is definitely going to leak something about K. It's not going to leak all of K. It's going to leak a very small portion of K. So now that we know how things can leak, let me switch back to what do we do with that leakage. So we already established the fact that if we have no leakage, then ECDSA gives us J equations and J plus 1 unknowns, right? So we have infinite solutions. It's not helpful. But with side channels, it's not exactly that bad, right? The situation is not that dire because we have J equations, but how many unknowns do we have? Yes, technically it's J plus 1 unknowns, but we know a little bit about each of those unknowns, okay? So can you somehow take all of that little bit of information? So how much of an unknown does all of that small stuff add up to? Okay, so if we know 3-4 bits of each nonce, how many of those do you have to compile before it basically substitutes for an entire unknown, in which case you would have J equations and J unknowns, and you would solve it with linear algebra. So the answer is we use lattices to solve problems like that, okay? So let's say we have J equations that look like this. So this is just the linear component of DSA, which has been reorganized, okay? We have J equations and J plus 1 unknowns. So what if we know a little bit of each of these K sub I, okay? We know a little bit. We don't know anything about D, but we know something, a little bit of something about these K sub I. So what we're looking for is a small solution to this linear system, okay? And that's exactly how what lattices are good for. There's a great paper from '99 by Nick and Nigel. If you haven't read this paper, you should go read it. It's very good. It's one of the few lattice papers that I actually understand. So let's see, how can this possibly work? How can lattices solve this problem for us? So it's J equations, J plus 1 unknowns, but we know something about those J of those unknowns. We know a very, very little bit. Okay, it works because of this. This is just a high-level concept for why lattice attacks work. Okay, so if we have a system of equations with J equations and J plus 1 unknowns, okay? Let's say you want to know what one solution looks like. So you just pick one of the unknowns at random. You're going to be wrong, right? But I just want to look statistically at like what the solution looks like. You pick a random value for one of the unknowns, and then you solve for the rest of the unknowns, okay? What are those other unknowns going to look like in terms of bits and in terms of length? Well, when you solve that system of equation, here it's a dimension 32. I guess it's 31. I'm unable to count this morning, it seems like. The idea is that half of these are going to have the top bit set as 1, and half of them are going to have the top bit clear, okay? And I think that makes sense. If you think the modulus is very close to a power of 2, the modulus looks like this, okay? It's very close to a power of 2. It's just under a power of 2. So then when you do this kind of solution, modulo n, half of them are going to have the top bit set, and half of them are not going to have are going to have the top bit clear, right? So now if we continue on from these that had the top bit clear, well, half of those are going to have the next bit set, and half of those are going to have the next bit clear. So this is kind of, you get this binomial kind of distribution, right? This makes sense, I think. Intuitively, this is what an average solution is going to look like, all right? And there are a bunch of these average solutions, right? Because that's exactly what they are. They're average. If you choose if you fix one of the unknowns to another random value, you're going to get another average solution that looks very similar to this, okay? The thing is that our average solution doesn't look anything like the one on the left-hand side. Let me go back to this equation. So if we take this equation and we rearrange it in terms of the K sub I, and then we split the K sub I into the parts that we know and we don't. Remember, we know a little bit about the K sub I. Then you end up with an equation in some new variable where the unknown part is somehow small. If you learn 3 or 4 bits of K, then the only unknown part of K is basically minus those 3 or 4 bits, right? So if you rearrange the equation like that, and you try to solve that system of equations, it actually looks more similar to the right-hand side. The solution we want is on the right-hand side, okay? Because the unknown part of the case of i's, they're small, because we already used the side channel to retrieve part of the case of i's, right? So the solution we're looking for to this linear system doesn't look anything like the left-hand side, because we want small. These are big, right? Half of these are full bit size. The other half or a quarter are like 1 bit less than full bits. This is not what our solution looks like at all on the left-hand side. Ours looks like the right-hand side. This solution should be very rare, right? If you think about the probability that you end up with a whole bunch of these small things, it seems astronomically small, right? So there should be very few oranges, and there should be lots of apples. That's the point of this slide. And lattices are exactly that thing that let you find the apple out of all of the, let you find the orange out of all the apples. We're looking for the orange. So that's it about lattices today. Lattices is an incredibly interesting topic. For an applied cryptographer like me, it's more like a black box, and that's what this slide is showing. Maybe 14 years ago when I first started using lattices, for sure it was a black box. I didn't know anything about lattices. Having now used them for many, many years, I know more. It's more like a gray box. So I'm able to poke inside the box a little bit to do what I need. But at the same time, I'm no expert, okay? But I think for people doing side channel analysis, and if you're an applied cryptographer, you can view lattices as a black box that you throw an underdetermined system of equations at it, and it will try to find a small solution to that system of equations. That's what lattices are useful for, okay? And I think another thing to take away from this talk is when you're writing code and you say, oh, this only leaks a little bit, you only need a little bit sometimes, okay? So, you know, lattices can succeed with 2 or 3 bits per nonce. So it's even a small amount of leakage can really end up being detrimental, essentially. Okay, so I think now I'm going to jump into the rest of the talk, which is more about the side channel work that I've been doing essentially my whole career, if you want to be honest. So the project that has been the focus of my research and my team's research for many, many years, this is since about 2008, is OpenSSL. So here's some text from Wikipedia for what OpenSSL is. Essentially, it's a very large software project, okay? So it comes in 2 parts. There's libcrypto, which does all the crypto bits, and then there's libSSL. Unfortunately, it's called libSSL, but it does the TLS parts. So it's a cryptographic software library that is also like a Swiss Army knife, to be honest. So what I like about doing research using OpenSSL is that when you end up with results, they have impact, right? So this is not a pure academic exercise. OpenSSL there are so many deployments I could not even venture a guess. But if you look at the bottom here, Census is an organization that gathers statistics about certificates. In this case, these are like X509 certificates, okay, with digitally signed keys, essentially. Let's Encrypt is one of the technologies that's catching on these days, letting basically everybody do certificate management for free. So that's why it's catching on. And I checked it this morning. The most up-to-date number I could come up with is 58.2% of all certificates on the internet are issued by Let's Encrypt, which is incredible. So one way to read that, and you know, Let's Encrypt is basically a bunch of scripting around OpenSSL at the end of it. I'm totally oversimplifying an incredible concept of Let's Encrypt, but that's what it is at the end of the day. It's a bunch of stuff written around OpenSSL to renew the certificates. That's what it is. So if you think about it that way, OpenSSL is driving almost 60% of the internet, which is really scary considering that 5 years ago, they had 1 full-time developer. So It's very scary to think that such a critical software package has so little support. It's changed a lot in recent years, but I'll get to that a little bit later. So the focus is mostly going to be OpenSSL here, okay? And again, the talk is about technical debt, especially with side channels. So I'm going to talk about design decisions for the OpenSSL software architecture that have led down a path that has taken so much, it has amounted so much technical debt that we're still paying it, to be honest. So side channels became a concept in OpenSSL around 2003. Okay, so it's about 5 years into the project compared to the previous slide. This is probably one of the most well-known papers about side channels. So remote timing attacks are practical. This is Brumley and Bonnet. That's not me, Brumley. That's a different Brumley. Right. So this is one of the best timing attack papers ever written, in my opinion. Mostly because it was a real end-to-end attack, which was very rare at the time, and it was a remote attack. I know the focus today, the talk after me, Daniel's going to talk about microarchitecture attacks and stuff like that. This one was not microarchitecture at all. It was just remote timing. So you open a handshake and you see how long it takes for the reply to come back. Anybody can do this. You don't need any special microarchitecture. You don't need any kind of special access or anything like that. So the vulnerability in this case, was caused by two different, actually conflicting, which made it super interesting, timing variations. One of them was, I have to think now, it's been a long time. Yes, it was how it handles multi-precision multiplication. So it takes different, it might do Karatsuba at some level, or it might do schoolbook at some level. And so this can tell you information about the operands, basically, by knowing how long these operations take. And then I believe the second one was the modular exponentiation function in OpenSSL had no concept of, through the entire library, there was no concept of side channels at the time, okay? So it was like shooting fish in a barrel. I'm not trying to insult the work. But yeah, there were no defenses back in 2003. Okay, so as a project, they get this report, of course, from academics. And how do you respond? Like, how should you respond to something like this at the software architecture level? So now it's very easy to look back and say they made the wrong decision, whatever that is, 18 years ago. It's very easy to say that now. But 18 years ago, I don't know. Maybe they thought they were making the right decision 18 years ago. Let's see what they did. Yeah, so two attacks kind of came in at the same time. Let me cover the second one. The second one was Colin Percival, Cache Missing for Fun and Profit. This is the best microarchitecture side channel paper ever written. So if you haven't read this paper, you should go read this paper. It basically talks about, kind of similar to the previous attack, which was attacking RSA. This is also applied to RSA, but instead of the remote timings, it focuses on microarchitecture timings. Essentially, the exponentiation function used in OpenSSL was variable time, and they were using L1 data cache timings to detect non-zero digits of the exponent in RSA, essentially, was what was happening. I really like the paper because it takes, I know there's students here on the call, so I did give you some advice. When you're looking for side channels, especially novel side channels. So, side channels, they come in all forms. It can be remote timings, all sorts of microarchitecture timings, like data cache timings, instruction cache timings, last level cache timings, port contention timings. There's the MMU, so the page table timings. I'm missing a lot, but there's a bunch of different timing attacks that you can run at the microarchitecture level. As a researcher, when you're trying to find new attack vectors, like, say, for example, L1 instruction cache, if you were trying to design a new attack vector there and say this thing is leaking, what you should do as a researcher is try to design a process that uses that mechanism to communicate on purpose. So you want to have kind of a sender and a receiver. It's called a covert channel. So you want to use, for example, L1 instruction cache timings to have two processes talk to each other. So the first step is to design the covert channel, okay? So what you do is you write these programs very specially so that they exploit the microarchitecture feature that you're looking for in such a way that they can communicate together. They're trying to communicate with each other, okay? And that's exactly what Colin does in this paper. And the way you turn that into a side channel is that instead of the two processes trying to talk to each other, you have one process that is desperately trying to talk to the other one, and you have one that has no idea that it's talking at all. This is the victim, right, that you're going to steal the key from. And then that's a very nice way to do that transition. So I think when I first read this paper a very, very long time ago, I thought that that was kind of a silly concept, but over the years, I'm older and wiser now, and I understand that that's the best way to frame the research. And I say it's the best way because if you cannot purposefully make them talk together through some microarchitecture feature, then there's no way it's going to happen by accident, right? So in terms of research methodology, it's a nice first step to take to make sure that they can talk via some mechanism, instead of getting way down the road trying to do your side channel and then realizing that somehow it doesn't work, or somehow the method you're using is not optimal, okay? Right, so you have two attacks coming in roughly about the same time, both against RSA. So how do they respond to these attacks? This is what the project does. The fact is that countermeasures to side channel attacks are costly. And sometimes at a software library level, you actually don't need the protection. So let's say you're doing digital signature verification, okay? When you're verifying a digital signature, everything is public. There's no such thing as a side channel attack, right? So there's no reason to pay that extra penalty for side channel protections for digital signature verification because everything is public anyway. So as a library, I don't think this is a good idea, but as a library, you might make the distinction between, for example, on this slide where it's calling exponentiation, is that exponentiation called in the context of this is to say security critical exponentiation, like signing digital signatures, or it's not security critical, like verifying digital signatures. So you might want to distinguish those things. And this is exactly what OpenSSL did. They added a flag to each of their, they added a flag to each of their big numbers, okay? And you have to mark these as security critical. So if it's some kind of secret, you can see in this case, it checks if P is a big integer here, okay? So it's a big number, multi-precision integer, and it checks if that flag is set in this big integer. It's just, there's an extra integer in the structure that's tracking flags, okay? And if it's set, which means this has been flagged as some kind of secret, then it calls down to this constant time function that costs more, okay? But it makes sense, at least it's secure. So that's the countermeasure. If you look at this, you've been looking at this slide for what, 30 seconds now, maybe you think this makes sense. And probably 18 years ago, OpenSSL thought it made sense too. When I look at it, it kind of makes sense. Until you know all the things that can go bad when you do this solution. And that's what I'm going to spend the next 10 or 15 slides going through. So they made this decision, 15, 16 years ago, that the way they're going to approach side channel vulnerabilities in OpenSSL is to mark secrets as truly secret. And then you change your control flow based on those flags, okay? Another approach would be just say, don't use a flag and do everything constant time. So why wouldn't you just do that? And this is what academics will tell you. They will say, oh, it should just be constant time. And they say that comfortably from their armchairs while, they're thinking really hard as academics. So the reason is that constant time is a lot harder than you think, okay? And it costs more than you think. So when you think about the context of an entire library, I would claim that it is almost impossible to create a modular exponentiation function that is truly constant time and meets the constraints for modern cryptography, okay? I say that because I will give you a very small example here. Let's say you want to verify an RSA signature. It's one of the fastest operations we know because you can choose the exponent to be small for the digital signature verification, right? So the exponent is very small and it goes very, very fast. But then you think about something like DSA or ECDSA signing. The better example is DSA signing. It's the finite field equivalent of the elliptic curve one that I talked about earlier. There, the length of those components is actually critical. So how can you have one function that meets both of those crypto needs? One of them has to be, you know, very fast and they have vastly different bit lengths, right? How can you have one function that can magically handle both of those things? It just doesn't exist. But you ask cryptographers and they'll say, oh, just make it constant time. It's very easy and dismissive to say that until you get your hands dirty with the code. My hands are completely dirty with OpenSSL code over the past 15 years. So yeah, I'm going to talk about all the problems with the flag. All right. So moving on from the RSA vulnerability, well, like the exponentiation vulnerabilities. So a couple of vulnerabilities popped up a couple years after Colin's work, also specific to RSA. These were called branch prediction vulnerabilities. And the idea there is if you branch on secrets, this also affects the microarchitecture state. The authors used this not for exponentiation. So we knew exponentiation was vulnerable. If I go back to the previous slide of the countermeasure, we're in the exponentiation function and we have some special control flow that will protect secrets, okay? But what about outside exponentiation? There's lots of places where things can leak. That's exactly what this work talked about. It wasn't specific to modular exponentiation. There are other functions that might leak too. In this case, that function was the modular inverse function. Okay, so if you need to compute the inverse of a finite field element, for example, I guess it wouldn't be a finite field element in this case because it's a RSA, but a ring element. Okay, you need an inverse of a ring element. Okay, so instead of having this flag called BN flag exponentiation constant time, now constant time is like a concept in OpenSSL, right? So it moves on from just being this exponentiation flag to this new thing just called BN flag constant time. So you're marking something as secret, and whatever functions get called in the call stack should somehow be checking that flag and trying to protect secrets that are marked as secret, which kind of makes sense as well. More technical debt piling up. That's what I will tell you, and we're going to get to all the ways this goes bad in just a moment. This is my work from 2009. So that code that we went through about how OpenSSL scalar multiplication function was vulnerable at least in 2 places to side channel attacks. It's actually more than 2 places. It's at least 3 places. The other one isn't important for the talk, but what you can see on the screen here, I have been staring at these dots for a very, very long time, so I'm very good at picking it out. You want to read this kind of from left to right, and this is 32 signals that are stacked on top of each other. You can think of it as a heat map, and that's how it's displayed as a heat map. This is L1 cache timings as that scalar multiplication function is executing, and you can see these 32 signals have been processed, and that's what the top rows, they contain metadata basically. So the black ones here indicate that it's doing some kind of point addition, and the white ones are some kind of point doubling. And the sequence tells you something about the digits of the scalar. Okay, so this is kind of what you would expect in terms of a double and add algorithm. So it adds and it does a bunch of doubles, and then it adds again and does a bunch of doubles. So this sequence that varies in terms of the number of doubles that are inserted between these adds, it tells you something about the scalar. So what you would probably be expecting after this slide is me saying how you go and set some flag and this just goes away. That's actually not what happens at all. this wasn't fixed, not in the way that you think it would be fixed. So there was no flag added to address this vulnerability. Basically, the ECC is a little bit different from RSA in that we have fixed curves for elliptic curves. All right. So what OpenSSL did is, instead of fixing the generic elliptic curve code, they started to produce curve-specific code that would get around this vulnerability. So a very common curve is NIST P256. So basically, OpenSSL took some custom code for P256 and integrated that into the library to avoid this vulnerability. And they did the same thing for P224, which is another curve, and for P521, which is another curve. The list goes on and on over the years, okay? So this wasn't fixed. I'll get to when it was fixed, but in 2009, it was not fixed. I will put it that way. And I'll get back to why it wasn't fixed later in the talk. Okay, so in 2010, this was my work at CHEST 2010. There was a vulnerability in the DSA exponentiation algorithm. So we went through RSA exponentiation, which had a vulnerability. We went through ECDSA, which had a vulnerability. We went through RSA key generation that had a vulnerability. Now it turns out that the DSA signing function also had a vulnerability that was very similar to the elliptic curve one, okay? And this graph is very similar to the one on the previous slide. What you're seeing in the sort of dark gray ones here are squarings. So this is modular squarings. This is a square and multiply algorithm. So it goes square, 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 and then the black are the multiplies. So the sequence of squares and multiplies tells you something about the scalar. It's a very similar kind of vulnerability. So how did the library respond? The answer is it didn't respond at all. And I'll get to why it didn't later, basically. So it's a little bit of a cliffhanger for why nothing happened with this code, but I'll get there eventually. So the next year, 2011, this is also some of my work at ISCwsISC. So for this vulnerability, what actually ended up happening, instead of actual digits that were leaking, this is a remote attack. So what is happening here, each one of these curves shows the distribution for ECDSA signing over the nonce length, okay? So if the nonce length is greater than or equal to 160 bits, we have larger timing. And we can see each one of these curves kind of goes down in timing, right, as the number of bits in the nonce drops, which kind of makes sense. It's faster for you to do a 159-bit operation than it is to do a 160-bit operation. And so on down the list. This is sort of, if you looked at this, I think it makes sense in your head, but then from side channel perspective, it's totally broken because you can't have these kind of dependencies. These curves should be on top of each other if it's constant time. Right, so there should be no difference between 160-bit scalar multiplication or 159-bit scalar multiplication. They should be, all these curves should be on top of each other, but they're not. They're incredibly distinguishable in this case, and we used it to recover a private key from a TLS server remotely, which was some very nice. There was some nice work at the time. Okay. What was the fix for this? The fix was to pad the scalars so that they were basically always on top of each other. It had nothing to do with the constant time flag. So basically, the fix was making all scalars 161 bits at the end of the day. Okay, I'm going to skip just in the, yes, I'm definitely going to, I'm going to skip bug attacks in the interest of time. Okay, so at this time around 2011 and 2012, not much actually happened in 2012 and 2013 in terms of side channel attacks on, at least on OpenSSL or Lattice techniques or anything like that, or microarchitecture techniques. Then in 2014, something very magical happened. So there was an attack and also a microarchitecture technique. use to implement that attack. The microarchitecture technique, which I think is very standard these days, is called flush and reload. So essentially what they did in this, so the flush and reload is a very, you should go read the paper. It's not the one shown on the screen here, but this was from Usenix, I believe. Yuval Yerome. It's a more flexible way to get the cache timings than what was shown in the previous slides. The most interesting thing about the paper shown on the slide here is all of the end-to-end lattice attacks. Basically, I was the only one doing them in academia at the time. All of those end-to-end attacks fixed the amount of leakage in each equation. So if I go back quickly to the ECDSA equation, all of the lattice attacks so far, because I'm an engineer and not a mathematician, basically would fix saying that you know 4 bits of K. Well, maybe you know 4 bits of K, but maybe you know 5 bits of K. Maybe you know 6 bits of K. Maybe you know 3 bits of K. So maybe you should actually use how much information you actually have instead of fixing the amount of information that you know. Unfortunately, the lattice constructions at the time didn't let you use all of the information you know, so I was doing the best I can with the tools I had. That was the most important thing about this paper, was that suddenly you could start to use all of the equations and not the ones that were filtered to leak a certain amount of bits, okay? And I think this is a great paper, and I'll tell you why. It has nothing to do with the actual vulnerability in OpenSSL. I don't really care about that. In terms of science, this paper is great because it led to improved lattice methods to better utilize the leakage. So what I'm saying is actually down in the actual lattice construction, when you construct the basis matrix, all of that varying information is accounted for how you build the system of equations, okay? And what's really neat about this is one of those conflicting things in academia, and let me make my point here. So the 2009 vulnerability, it's the same code path, okay? It's the same code path. The 2009 vulnerability was never fixed. So what I would say is I don't think that the paper that you're seeing on the screen here now, which in my opinion is one of the most important papers for lattice-based cryptanalysis, I don't think this paper would exist if the vulnerability would have been fixed in 2009. Okay, so the fact that nobody fixed it in 2009 or 2008, it is a very strange situation to think that way, but the way I think about it is the fact that nobody fixed it makes this paper possible. So I don't think this paper ever gets written if the vulnerability gets fixed back in 2008 and 2009. So it's a very, we all want science to progress, but we also want security at the same time. So it's a very, what are you supposed to do as a researcher? It's very, it's conflicting, right? So should you leave the vulnerabilities there so that you can churn out more theoretical results? Or should you go fix them? That's the ethical thing to do, right? It's tricky decisions, okay? But I love this paper. It's this is when the gap between, so you had, people using lattices in a very silly way, which was me back in 2008, 2009. And then suddenly, as of 2014, academia started to adjust. So you had people who know more theoretically about lattices are able to modify their constructions to better model the leakage that we're seeing in the real world. So you have these things coming together, right? You have theory and practice, and they're starting to converge. So it's a very exciting time. So after that work in 2016, there was a paper at CCS 2016. This was one of my students, Cesar Pereira Garcia. So there was a vulnerability in OpenSSL's DSA signing function, and actually we know that vulnerability already exists because I showed this plot. So it's the same vulnerability. Of course, you can't say that in a paper, otherwise they're going to reject your paper. So the technique changed a little bit. So what was interesting about this work is that if you look at the code for DSA signing, it should never actually have hit the insecure code path. So there's a if you remember the flag that you can set where it will take a secure path for exponentiation, DSA should be doing this, because if you look at the code, the flag is getting set, and then if you look at the call stack, it should go on down a secure path, but it actually ends up going down the insecure code path. And that's why nobody ever fixed it in 2010, because I think it was dismissed. They looked at the code, and it looks like I have done something like unethical, basically, like making the vulnerability possible, which is, I didn't know why the vulnerability was happening back in 2010, but I just knew it was happening. And that's exactly what this work finally root caused it in 2016. It was because when you were copying the big numbers from one to another, it actually wasn't propagating the flag. So you could mark something as a secret and then copy it to a new big num, which is magically going to lose that secret flag. Okay, so then it just gets treated as a normal scalar, which is like facepalm, right? So again, another failure of those architecture decisions that were made back in 2003 and 2004. If you're going to have everything driven where it's insecure by default by a flag, then this is exactly what's going to happen. The failure scenarios are going to fall through to side channel insecure code. Okay. To explain this one, I have to go back to the equation for ECDSA. So I'm going to flip back really quickly and we'll look at ECDSA again. So far, I've been talking about leakage down here, right? So it says we're leaking during the scalar multiplication for producing this R. It turns out that's not the only place where ECDSA or DSA can leak. So it turns out in the S component, when we invert the nonce here, it turns out this inversion can also leak something about K. So even if you're doing something constant time here in terms of scalar multiplication, if your inversion routine is not constant time, you can leak something about K here. And that's exactly what we did in, I think, 2017 at Usenix. This one, yes. So instead of, square and multiply is for exponentiation. For inversion, it's the extended Euclidean algorithm, which in this case is a series of shifts and subtractions, okay? And so that's what this signal is showing, is that the blue parts are the shifts, the blue parts are the subtractions, and the yellow parts are the shifts, okay? You can see that subtractions are always separated by at least one shift operation. Here we have one shift, subtract, two shifts, subtract, shift, subtract, and so on. This sequence leads you to, again, partial information on K, essentially, and you have a lattice problem all over again, all right? Why did this vulnerability exist? Because the flag was not set, right? So if you look at the fix, I don't show it on the screen here, but the fix for this, I wrote the fix, and the fix for it is to set the flag on the nonce, okay? Okay. So I'm going to pause here for a minute and talk a little bit about the fix that went in for inversion. So if we look at what's on the screen here now, the fix for this basically rerouted the function call to a side channel secure version of modular inversion. All right, and that function is literally the one that was from ISCwsISC's vulnerability back in 2007. So it actually ends up taking the same code path from 2007. Okay, that's what the fix is. So what I want to do right now is actually go through this function, which is supposed to be the fix. It says this bn mod inverse no branch. Well, that sounds promising if you're trying to prevent branch prediction attacks. If there's no branches, that sounds very promising. Let's go look at that code. So this is that code in OpenSSL. Let me scroll up. So bn mod inverse no branch, it inverts a modulo n. That's the idea. So I'm going to scroll down to the main loop, and this is the main loop. And basically what it is doing in this loop, I'm not going to go through it, but this is the traditional Euclidean algorithm. So if you think about the traditional extended Euclidean algorithm, it's a bunch of divisions and modular reductions is basically what happens. So you see where is it? I missed it. Here it is. So you have the divisions here, and then based on the quotients, you do some multiplications, and it says additions here, but these are just inverted, so these are actually subtractions. And that's exactly how the extended Euclidean algorithm executes. It's, you reduce one of the parameters modulo the other parameter. So this looks good if I look at this. These are not actually branching on secrets. If I look, these are just assignments. This is checking the return code, which is it's a constant, so there's nothing side channel vulnerable here. This looks good. The main loop ends here, so let's scroll up. Again, this looks good as well. And bndiv has some countermeasures, it looks like, because we're setting the constant time flag. So here is the major problem with this function. The entire loop is the entire loop is bounded by a branch. It says while not bn is 0. So as researchers, if you're getting started in this field or you're interested in this field, this is like a freebie that I will give you right now. Okay, if you want to write a paper, study this function, because nobody knows. Everyone who does side channels knows that this function is vulnerable. What actually happens when this function gets called is it tells you the number of loop iterations that it took to compute the inverse, okay? Which, if you know the number of loop iterations, it tells you the number of divisions that took place, basically. So how can you turn the number of divisions that were performed into information on the inputs to this function? So nobody knows, everyone knows this function leaks, but no one knows how to actually use that information from the theoretic point of view, okay? So this is not an applied cryptography problem, or I would have solved it a long time ago. I don't know the math to solve this problem. So if you want a free problem that will for sure give you a good publication, study this function, where the goal will be, how can we, by knowing the number of iterations in the extended Euclidean algorithm, what does that tell us about one of the unknown inputs to the algorithm? From the theory perspective, we just don't know. So I can get that information for you. Like I can easily provide that at the microarchitecture level, at the remote timing level. I can tell you, here is some data, and with this specific inputs, it was, X amount of iterations. I have no idea what to do with that information. But from the theory side, if you can tell me that, I guarantee you there's a good paper waiting for you there. Okay.
Billy,
Sure.
can we interrupt here? I think, thank you for your interesting presentation and the details. Actually, we have one question by Milad, and I have a question too. I appreciate if we can have answers of these questions, please. Milad, do you have your microphone? Can you use your microphone to ask your question? Or should I ask Billy? I can allow you to use your microphone if I find your name in the list. Milad. Please raise your hand if you want to use your microphone. Otherwise, I will ask Billy your question. Okay. You see the question here. I repeat it for a record. After the advent of modern microarchitectural attacks like Meltdown, Spectre, and so on, is the implementation of flush plus reload attack on encryption algorithms valuable? What's your opinion, Billy?
So it's a really good question. So to rephrase the question, basically, if you can use speculation techniques like, for example, Spectre and Meltdown here to just glean the information directly, do you need side channels anymore? I think these are orthogonal problems. I think so. You can tackle. So you have side channel security going here, right? And then you have speculation security going here. And these, of course, they overlap sometimes. These techniques are very related, and I guess Daniel will get to that in the next talk. But I think these are problems that should be tackled independently. So I guess my point is, once we have solved problems with Spectre and Meltdown, it doesn't change the fact that you still need side channel security to avoid things like flush and reload attacks. I hope that answer makes sense. So in a magical world where we have solved all the speculation issues, the side channel issues still persist, right?
Milad, your microphone is enabled and you can ask your questions if anything is unresolved on your side. Okay, it seems Milad doesn't want to talk with us. Okay, now my question here. If I could understand correctly, the problem here was that the flags were not treated correctly. If the treatment was complete, for example, when copying one big integer into another, the flag correctly be copied, would the problem be solved, or there is an inherent vulnerability in this kind of treatment? Am I
So it's a really good question, and I'm glad you asked it. So it is true that the fix, if I go back to the, I think I should go back to the 2016 one. Okay, the fix for this vulnerability, exactly, it was literally like, you know, don't throw away the flag when you're copying things, right? So you can say that, yes, that is the fix. It was like a 2-line fix, okay?
yeah.
But in my opinion, there's a concept of secure by default, okay, going in computer security, going all the way back to the 70s. And if you look at this, how OpenSSL is using the flag, it's not secured by default. Basically, it's defaulting that if you just grab a big integer and use it, it defaults to the insecure behavior. So if OpenSSL, I'm not saying this is the right design decision, but one way they could have done it is to invert the logic to say, I only take the insecure path if I've been told explicitly to take the insecure path. Then we would have avoided this vulnerability, because even if the flag, basically at that stage, you have to go through your code base and find the places where it's okay to relax the flag, like verification. So it just inverts the logic, right? So I think having a secure by default where it always takes the secure path unless you have told it explicitly would have been a better solution than what they have done.
Yeah, it's it's less prone to errors and bugs. Yeah.
Exactly, and you're talking about a huge code base, right? So who's going to go through that code base and find all the places where you're supposed to set this flag to keep security, right? I just went through like 10 different attacks where basically either the flag was not set properly or it was mishandled. So it's not a good approach, I can tell you that.
Okay, thank you very much. Is there any questions here we can answer? Please raise your hand or write down your question in the chat box, please. Okay, we don't have any questions now. Okay, sorry to interrupt you. Could you please continue?
Yeah, absolutely. And again, if any questions come to mind, you know, you can I'll still take some more questions, I guess, at the end. So here we go. Okay, so the next attack. Give me 1 second. I think someone is not on mute. Can we?
Oh,
thank you. I appreciate it. Right. So we had this previous vulnerability on inversion in ECDSA. One of the next works was by one of my students, Cesar, as well. This was on RSA key generation. So if I go back, sorry about flipping back and forth so much, but if I go back to owner's work here, basically what you're seeing here, it was a microarchitecture attack on RSA, but it wasn't for key generation. It was for something else. Yeah, I guess it was maybe for RSA encryption if I have to, or I guess it would be decryption if I have to guess. So the main vulnerability there was reaching a modular inversion function, the insecure version of a modular inversion function, okay? So in 2018, we were able to do the same thing, but not for RSA decryption. It was for RSA key generation. So when RSA keys are generated, it has to make several calls to either modular inversion functions or GCD functions, which are essentially the same thing, right? So the fact that, this is again another place where it wasn't marked as a secret in the code, the conversation we just had in the Q&A, right? You have to go through the code base hunting and finding all these places where you're supposed to mark this magic number as a secret. So, okay, well, in 2018, they forgot another one. It was RSA key generation. So there we go. We had a vulnerability there. What you're seeing on the screen here, the top is the actual raw cache timing trace. You're seeing 2 exponentiations. That's why you see kind of the 2 blocks. The second graph here is the template. So kind of what happens here is, you see this, I'll just tell you a little bit about the microarchitecture techniques that I use here, so that we use here. You basically build a template, which is in a lot of cache timing data, you're looking for one specific thing. So we wanted this block that looks like this in the second graph, okay? So once you have a template, you just match it against the pattern. And the third graph here actually shows the Pearson correlation. So you can see it has 2 peaks basically, right? And that basically correspond exactly to those chunks that we are looking for, right? So this is basically how it works. You build a template, you try to match that template versus your trace data. And when you see peaks in the correlation, that means you found what you're looking for, all right? Right, and the bottom one is actually showing a zoomed version of one of those tiny black boxes, one of the 2, basically. And it's a series of shifts and subtractions. Again, it's the same code, just exploded in a different context. So the fix there was, of course, very boring. It was go set the flag. So eventually around that time, me having been involved in a lot of those works in OpenSSL, I get tired of, I don't want to, it's so frustrating just finding new places like where these vulnerabilities keep popping up basically because of the flag, right? So this is again the technical debt. What we decided to do was make a tool that will actually just detect this. Instead of doing this analysis manually, which is what we had done for the past, I don't know how many years, we wrote a tool that will do this analysis automatically, semi-automatically. It's called trigger flow. The idea with trigger flow, there's a screenshot here, but we can just go to the project page. It's open source, so you're free to use it. In the context of OpenSSL, basically what it does is it tracks the public repo of OpenSSL, and every time new commits get pushed to OpenSSL, it tests that against what code path should actually be executed. So we shouldn't hit insecure code paths for certain operations like digital signing, key generation, and stuff like that. Verification, it's fine, but not for signing. So the way trigger flow works is it maintains a set of patches for the code base. I'll look at the scalar multiplication just for example. No, that's not a good one. We've been talking about inversion, right? So I'll bring up that one. Right, so we can see the very top part of this div, it's the modular inversion function, and it's checking the flag. It doesn't show it here, but it's checking the flag right here, and if the flag is set, it's calling this no branch thing, okay? But if it reaches down here, we know that the branch was not set, right? And so we actually annotate OpenSSL with a comment that says POI, which means point of interest. So if we hit this line of code in a security critical context, we know that something was not set correctly because we should have early exited here, okay? So this is exactly how trigger flow works. We maintain a set of these annotations. When all of this happens automatically in terms of once the patch is constructed, okay? So every time OpenSSL is pushing to their repo, this project pulls that source code, applies the patches, and runs all of our unit tests to make sure nothing broke, okay? So the unit test it actually runs, we have a full test suite. It's the reason the tool is called Trigger Flow is because there are triggers that do different interesting crypto things. You can see this is a bunch of OpenSSL command line stuff that does different things. It's commented. It does things like generate keys, encryption, decryption, and digital signing, okay? And Trigger Flow is going to watch in the debugger while OpenSSL executes these security critical things. And if it sees a code, it sets breakpoints at these insecure code points, and if it hits those breakpoints, that's probably a vulnerability. That's how Trigger Flow works. So luckily, it's been several years since we have seen that kind of vulnerability in OpenSSL anymore. We're trying very hard to deprecate the actual flag, constant time flag in OpenSSL, but it takes a lot of time to do that. Again, it's the technical debt. Okay, Trigger Flow is not a tool that's unique to OpenSSL. Okay, you can use it for any project that you want. And their CI, all of this happens automatically. So if we go to the pipelines, you can see that's eventually. So 3 days ago, I guess, was the last push to OpenSSL. But the pipelines are passing right now. So all the tests are passing is what that means. So that's Trigger Flow. You know, so the hits just keep on coming for OpenSSL. I'm very used to the code base. You're probably asking, what is SM2? I don't really know. It's some kind of Chinese standard for cryptography. You know how each nation, they usually have their own, I don't know if you have one in Iran, like your own kind of domestic crypto standard. This is the Chinese one called SM2. It's Elgamal-based digital signature, basically. This was integrated into OpenSSL in 2018, and exactly, you have to think, someone comes in with this new crypto system and tries to integrate it in OpenSSL, and they don't know the long history of what all the side channel attacks on ECDSA. They don't know about setting these flags. Like, none of this is documented. So they do what is pretty much a textbook implementation of SM2, and they drop it into the code base, which makes sense. And then it's just vulnerabilities everywhere because they don't know where to set this flag. They don't know when to set this flag. They don't know what needs to happen. This is a horrible approach at the software architecture level, right? Because you should be able to do that. You should be able to take a reference implementation of SM2 and drop it in, and I think reasonably expect that you don't shoot yourself in the foot with side channels. The library should take care of that for you. But it's not going to happen, of course, if it's this flag-driven thing. You have to know where to set it. It was a disaster. My team started to get heavily involved in the OpenSSL development around this time. I've been contributing to the project for, since 2008, but it was just here and there. In 2018, we became much more active. What do I mean by that? I think when I was talking about the initial ECC vulnerability that was never fixed in 2009, if I ask you why it wasn't fixed, the answer is, as a young researcher, if you're a young researcher in the audience now, I know what you're thinking. You want to break stuff, you want to attack stuff, and that's what you want to do. And here's what I think, here's what you're thinking. You think I will just report these vulnerabilities to the project and they will just fix them. That's never going to happen, okay? So, and I would say it shouldn't happen because you are the expert. We're not talking about a buffer overflow, some kind of traditional software vulnerability, right? We're talking about a side channel attack. So if you expect someone who couldn't actually write the code to be securely to begin with, if you expect them to be able to somehow come and magically write a mitigation, it doesn't work that way. So you're going to be wrong. I was wrong for 10 years almost. So that vulnerability was in the code base for 10 years and it never fixed. Guess how it actually got fixed? I fixed it, and my team, we fixed it together, okay? So it's not like the project magically decided this is important. We put in the work to fix it ourselves. I know that's not so exciting for you as a researcher because you want to break stuff, but fixing stuff is a necessary part of the research process, and I would hope that you can accept that early in your career so that it becomes part of your research methodology, right? You're not just breaking things, you're there to fix things. That's your primary goal, all right? I'll get off my soapbox for a minute. All right, so ECDSA, we had another attack and at the end of 2018, 2019, this was port smash, right? This vulnerability is not really, basically we had a new microarchitecture technique and we needed a vulnerability that matched to those characteristics of the microarchitecture technique. So when you have been working with OpenSSL so long, you can find stuff like this. So you have some attack vector and then you say, we need a piece of code that is doing this in an insecure way. OpenSSL will almost always provide you an example of that. So that's what's being shown here. This is the same code path, nothing has changed. So yeah, this is again around the time that my team started to get involved. 2020 at Usenix, so this is a vulnerability in OpenSSL in 2019. The thing is, if you look at, I'm going to go back to the previous remote timing attack on OpenSSL, which was from 2011, and you saw that the distributions of the bit lengths were clearly distinguishable, right? So the lower the time is, the shorter the bit length is, the higher the time is, the higher the bit length is. Literally 10 years later, it's almost the exact same graph, just slightly skewed. So if I switch forward to it, this is 10 years later. We found another vulnerability that allowed you to bypass the countermeasure that was in place 10 years ago. You can see these distributions aren't as distinguishable as the other ones, but clearly they are not on top of each other, right? These are different. So it's frustrating for me because this was also my work, part of my work at Usenix with my team, and like, still hitting the same code path and the same vulnerability 10 years later. Like, what is going on? You feel like, you're in a cartoon or something. So, okay. I think, at that stage, I can very authoritatively say that using the flag is the wrong way to approach it. We're still paying the debt in OpenSSL. These problems are not unique to OpenSSL. So here's some of my team's work from last year at CCS. This is on NSS, which NSS is the crypto library that drives, for example, Firefox. This is the exact same vulnerability from the previous slide. You have longer bit lengths taking longer time. This was a DSA remote timing attack. What you'll notice about this is the curves are very crisp here, right? So they're clearly distinguishable and they are so vertical. This was the cleanest remote timing data that I have ever seen in my career. And the attack was, very easy because these distributions are so distinguishable. How can we still be dealing with bit length vulnerabilities, 10 years down the road? Oh my gosh, like it's so frustrating. Some of the more recent work, 2021, this is from this year, so we're now caught up, I guess, in terms of microarchitecture techniques. We talked a little bit about flush reload in the break. One of the techniques that's paired with flush and reload is called degrading. If you're interested in degrade techniques, then check out this archive paper is what I want to say. Basically, traditional side channel analysis, when you're doing like power analysis, if you want to get better granularity for your signal, you use a better oscilloscope, okay? So you move from 500 megasamples to 1 gigasample. You move from 1 gigasample to 2 gigasample. You just keep increasing the granularity with your scope. Microarchitecture attacks, you can't do that because you don't have a scope, okay? So how do you make your SPI process, how do you make your flush and reload run faster? You can't make it run faster. It runs at the effective clock rate of the CPU, right? You can't make it run faster. What you can do is you can slow down the victims, all right? And that's exactly what degrade does. So instead of speeding your stuff up, you slow the other stuff down, and effectively you're stretching your signal, all right? Hyperdegrade is a nice technique that is much more effective than the original degraded technique. These are both well, degrade is like a standard technique now with flush and reload. Okay. The attack that we have is actually on Diffie-Hellman, applied to CMS. So if you're interested, yeah, go read the paper. I think it's interesting. This builds on the Raccoon attack, if you've heard of it. If not, go read that paper as well. Raccoon attack is a Usenix 2021 this summer. All of the Lattice attack stuff that I've been talking about mostly is for DSA, so it's digital signatures. What is really interesting about Raccoon attack is it shows how to attack fixed Diffie-Hellman shared keys. So I think that's super interesting from the theory perspective, because for so many years, we've only been attacking DSA style signatures, right? Which is super boring in the end, after doing it for as long as I have. So what's neat is to see the theory shifting for how to formulate leakage for Diffie-Hellman in terms of a lattice problem. So we can switch crypto systems now. So it doesn't have to be just DSA or ECDSA. We can attack Diffie-Hellman as well, which is super interesting. So now I'm just going to try to wrap things up. I know I'm running a little bit short on time. So lessons learned. Stopgap countermeasures brought you in the end. This whole talk was about technical debt, right? So if we could roll back time now, and I would totally tell them to take secure by default behavior with the flag, like we discussed during the Q&A. We already told you as researchers, you shouldn't be focused on breaking things. You need to fix stuff too. Researchers have a tendency to focus on crypto in a vacuum with side channels. What I mean by that is crypto is all about use cases, right? So I think studying the side channel properties of crypto in isolation is not the full story. I say that because crypto is part of some protocol. So if you look at most of the attacks, the trend now, and I'm glad to have helped started this trend years ago, is that we focus on end-to-end attacks, so system level attacks. So if we do a side channel attack on everyone I just went through, it's not like we time the function in general. I mean directly. We obtain the traces as part of executing the protocol. So we actually run TLS and we collect the messages. We don't actually time the lower crypto bits just in isolation, okay? So attacks, you should think about them from the system level. And I say that not because it makes it more practical, but because you can find out interesting things at the protocol level which affect side channel attacks. And I think that's where you can find interesting things. OpenSSL, you know, I used to bash on it all the time back in the day. It's totally different since 2013, 2014, when Heartbleed came along. There's a lot of developers there. Things are much more fluid. There's a lot of testing. It's like a real software project now. So if you want to contribute, it's a very different project now. So don't let some opinion you have from OpenSSL 5 years ago, it's changing all the time. It's getting better every day. If you want to contribute to OpenSSL, I will help you. My team is very involved there. So we're happy to help you bridge your academic results into the real world. When you do responsible disclosure, which is when you find a vulnerability, you're supposed to, whatever product it is, you're supposed to bring it to the vendor first before you go public. Okay, this is the ethical thing to do. So as a researcher, note that first. When you do bring it to the vendor, you should really show them your data. So they don't want, in my opinion, doing an on-paper analysis is of limited value to them. So it'd be very nice if you can bring them mature data to show them what you have tried and tried to exploit, not just pointing at some line of code and saying that is not constant time. That's not enough. So I think that's it about OpenSSL. Future work, I already talked about trigger flow. Even the other crypto libraries like NSS, I talked about that a little bit. My team is starting to branch out and to try to be less OpenSSL centric. We had some plans to redesign the OpenSSL elliptic curve module, but for licensing issues that unfortunately didn't work out very well, which sucks. I can talk about that though. Let's see. If you are interested in tooling that can provide you complete constant time full stacks of elliptic curves, we have a tool called ECDSA, and that's exactly what it does. Basically, you plug in the curve parameters. I'm sorry it's so small here, but you have things like P and the curve coefficients A and B and the generator coordinates, blah, blah, blah. You plug in those fixed parameters, and it will generate constant time, a full constant time stack for you. So, and it's part of it's formally verified as well, which is very nice. ECDSA is actually used in NSS now, so a lot of the elliptic curve cryptography that happens under the hood in OpenSSL is implemented by ECDSA. But hey, I'm pretty much running out of time, so I'm going to stop here, and I hope you enjoyed my talk, and if you have any questions, please just fire away.
Thank you very much, Billy, for your very interesting presentation. We have 2 questions in the chat box. I asked the questioners if they want to open their microphone and ask their questions orally. Please raise your hand. Otherwise, I will read the question and ask Billy. Okay, we have 2 questions, one by Mahdi Esfahani and the other by Milad Sadiq. Mahdi asked that if the attacker doesn't have any information about the offset address of the encryption of victim, how can the attacker get the offset address?
So it's a good question. It depends on, are we talking about, I will just make a guess. If we're talking about flush and reload, the answer is because the application scenario for flush and reload is shared libraries, right? And if you say you don't know the address, actually in a shared library, you do know the address because you're using the same library as the victim. This is it's a shared library, right? So you're both linking against the same binary. So you can just go look at the binary and find the offset that you want. Exactly how you find that offset, it depends. Academically, it's fine to compile a binary with debug symbols and just look at it in a debugger. Of course, in real world, you know, you shouldn't ship binaries with debug symbols. So there you would have to use reverse engineering techniques to try to find out the addresses that you're interested in. It's not really like, it's very tedious. You can do it. You just, basically you step through your code in a debugger, but instead of debug symbols, you're looking at assembly. Eventually you reach down to the function you're interested in after reading a lot of assembly, basically.
Yeah, thank you. But I think if relocation techniques are applied to the address, the parts of the binaries, this would change the offsets. Am I correct?
Hey, that's a really good, you know, my student lost about a month on that question that you were just asking. And so one of the things that you'll see, for example, ASLR, address space layout randomization. So you're going to get, you know, the virtual address you have for the library is going to be different from the victims, right? But what's interesting about the CL flush technique is it takes a virtual address. So when I flush my virtual address from my view of the library, it actually drills down to the physical address, and the physical address that the victim has is the same as you. So it actually, your inputs to CL flush are the virtual address that will affect eventually the physical address that both are using, if that makes sense.
Oh, so the problem remains and it does not mitigate the attack. Okay, the other thing, Mahdi, Milad asked that after the implementation of flush plus reload attacks on OpenSSL encryptions like AES, RSA, and so on, why doesn't OpenSSL mitigate flush plus reload attack on such encryptions for the latest releases? Why doesn't OpenSSL perform such encryptions without any leakage?
It's a very good question, and the answer is because it's a very complicated software project, okay? I think it's very easy for academics. I think I mentioned this in the talk. I'm not trying to criticize, but I think from the academic viewpoint, a very common thing to say when you hear about these vulnerabilities is, oh, just do it in constant time. And I hope my talk today has shown that it's just not that easy to do it in constant time. most of the developers for OpenSSL, they're not side channel people, they are not cryptographers. So why doesn't OpenSSL do it? The answer is, one is they don't have, you should be doing it. So why don't you do it? OpenSSL is a open source project, so you can go contribute to the project. So they're not technically the right people to be doing those mitigations. I would say most of the places there are mitigations in place, but if you think about OpenSSL, it runs on so many different platforms. So to sit there and say, oh, this is side channel secure, even code that I have wrote has been attacked in academia for OpenSSL, okay? And I do this for a living, so I don't see how OpenSSL developers can do any better than that. It's always constant struggle to improve the library, I guess is my point.
Thank you. And Siavash asked in continuation of Mahdi about regarding ASLR in OS, and I think you already answered this note. And at the final thing, I would like to mention that, as you mentioned, the philosophy or the idea behind open source software is that if you find something, okay, just go fix it. And I think after Heartbleed attack, we are seeing problems in a large scale deployed open source software. And I think the correct decision was to support OpenSSL with much better contributors. And I think this path should be taken for other widely deployed open source software. And I think it's the responsibility of big companies, big software companies, which rely on open source tools, open source software, open source other things that support good open source software in favor of humanity, I say. That's it. What's your opinion?
Yeah, I think it's a very well stated comment. I couldn't say it better myself. So when we talk about open source software, I think everyone has, especially the security critical. OpenSSL is an easy example, but you're totally right. What about the rest of, it could be NSS, it could be SSH server, it could be bind, it could be, DNS servers, stuff like mail servers. These are all security critical, and we all have an obligation for that. I agree that I think the bulk of that hopefully falls on commercial companies. I like that idea, and I think in OpenSSL you see it a lot. The downsides there is that if there's not enough transparency in the project, then having companies come and fund the open source projects, it can lead to situations where stuff gets put into the code base and you start asking, why was that put in? Is it because they've made big basically threw a lot of money at the project, or what? So sometimes you can end up in conflicts of interest. So I think a lot of the open source development, especially for the security critical products, I think part of the burden also falls on governments as well. So I think that states should be contributing as well to these projects. But yeah, I guess that's what I want to say. I think you said it very well, and in a perfect world, that's exactly how it would go.
Thank you. And Siavash has raised his hand. Siavash, I allowed you to use your microphone and webcam. Could you please? Yeah.
Yes. Thank you, Sadaf. Hi, Billy. Thank you for your great presentation. I have one question regarding. I don't have very I can say clear idea regarding timing attack, but one question raised in my head. I want to ask that one. I'm thinking, what is the idea that if we implement one software that regarding some branch that we have some else there, that regarding some else we consume times approximately equally with if block. I'm telling, for example, The problem that you catch it in the software and attack, as I understood, I'm not sure, maybe I'm wrong. As I understood, you catch the problem of, for example, if takes 2 seconds, for example, if takes 2 seconds, but we don't have any else. So it means that if we are here, and based on the times we understood that, okay, we go through to do the if block. I mean that what is the idea to implement the software in the way that we have some else block that is completely symmetric with the if in the time I can say vision. I mean, it is symmetric in the time consumption. What is the idea regarding this one?
Yeah, it's a good question. I argue with hardware people about what you just said all the time, because in a way it makes sense. Basically, you're saying you balance the branches, and then there should be no timing difference, right? Because it either takes one or the other branches. And okay, from a hardware perspective, what you said makes sense. From a software perspective, it's the wrong thing to do. For two different, I agree, in a remote timing situation, maybe it's not so important, but I will tell you 2 ways that is probably bad. One is you still have a branch, right? So you're affecting the microarchitecture state every time you branch on a secret. So you still have a branch which is affecting microarchitecture state, which you should not do. The second is, if you look at flush and reload, if those 2 segments for the, I'm trying to, on the screen here, if those 2 segments for the balanced branches, basically they'll probably map to 2 different cache lines. So if you're doing flush and reload, you can actually more granular focus on the individual branches. Okay, so it's probably not the best solution for you.
Okay.
But I agree, in the remote, these are not huge concerns for remote timing attacks, because you don't have any of that microarchitecture stuff. All you have is, I sent a message and it took this much time, right? So those can be quite effective for the remote attacks, I will say.
Okay.
One of the things, it depends on the crypto system. One of the things that I see people propose a lot is, oh, well, why don't you just add some random time to the response? And depending on the crypto system, the problem with that is, if the time, if it's, you can think about this random thing that you're adding, it's like Gaussian noise. Right. So, and what we know about Gaussian noise is, if you have enough samples, you can compensate for it with statistical methods, okay, and signal processing methods. So, depending on the crypto system, that countermeasure is not as good as you think it is. So,
thank you. Thank you.
Okay, thank you very much for your very good presentation. I learned a lot. And I'm sure that the attendees have learned a lot too. Thank you very much, and I think we can conclude our session.
It's my pleasure. Thanks again for the invitation.
You're welcome. Thank you very much. Okay, I think the next session of our our talks starts about 20 minutes in 15 Tehran time. Thank you for your attention, and goodbye.